Hello and welcome back to Calculus 2. Oops.
Just like do over.
Do over? All right. I'm not going to edit this. Hello and welcome back to Calculus 2 section 6.8 exponential and logarithmic functions. So in this section we are going to redefine these functions in terms of calculus. So we're going to use integrals and take a look at some properties. And then after this section, we'll do one more section that will be applications of those, which you probably covered, well, you should have covered in your pre-calculus courses. So I am going to start with exponentials. Even your book does it backwards. And I'm going to first define number e, which is defined as the limit as n goes to infinity for 1 plus 1 over n to the n. So this is the calculus definition because we have a limit there. And knowing this clearly gets us advantage when we have to solve certain problems. Now I'm going to write a modification of this so that we don't get issues later on. And this modification is that e to the r is equal to the limit n goes to infinity 1 plus 1 over, oh sorry, not 1, r over n to the n. And I'm going to box this one as well, because it will save you a lot of time when you run into a limit of this kind later on in this course. And maybe give a quick example here. So if you're looking for the limit as, let's say, x goes to infinity of 1 plus 3 over x raised to the x, you immediately write e cubed. Immediately. And just walk away. Because you memorized the definition for e, and you're realizing that if this r is 1, that is just e. If the r is anything else but 1, that r is the exponent of e. Now we will discuss this eventually in class and figure out how and why and what. But right now, that's it. Now, I just defined e in terms of the limit, which is the way it's actually defined. But then we can also define this e in a really weird way, which is through the integral of ln, which really makes no sense at first. So we'll build up to that point and we'll get there. Just want to make sure that. Okay, great. So let's talk about this ln business and then use it to define everything else. So how do we define function ln x? You define that as the integral of from 1 to x of 1 over t dt. You can use any other variable other than x. We call that dummy variable. So this is your definition, actually. You know when you integrate 1 over x, you get ln x, right? So in this case, you will get ln t. You have ln x minus ln 1. ln 1 is 0, so it's just ln x. So this is the definition. Now, interestingly, you can use this definition to show all of those cool properties like ln of x times y is ln x plus ln y. you can actually prove all of those formulas with this, using the properties of integrals. And you know, the honors section, that's what they actually do on the tests and so on. So you might want to look, if you have interest in mathematics and you want to go push further, maybe take advanced calculus and so on, you definitely want to look into those. I believe they did one of those in a textbook. They're not hard at all. It's just if you have interest in mathematics, go ahead and see how these are used to show all of those three important formulas. So properties of logs, which you did use and review in your Calc 1 when you did logarithmic differentiation. Properties of logs are that the log so ln xy is ln x plus ln y, ln x over y is ln x minus ln y, and ln of x to the p is p ln x. So these are the properties. And the one on top was the definition of a logarithmic function. Actually, yeah, they did one of these. So those are the basic properties. Now let's take a look at what's happening in terms of derivatives and integrals. So what would be the derivative of ln x? 1 over x. Great. Now let's upgrade. What is the derivative of ln of f of x? Yep. And then the boss of all of these, this is the most general case that you can bring up ever. What would that be?
fx ln a? Oh.
It's very close. So let's just quickly take a look. If the base is e, then that's this problem, right? In this problem, if this f of x is x, then it's that problem. So technically, I should be able to answer log base e of x and get 1 over x in this formula. And I will. Because, look, if log base a is e, then this calculation here is ln of e, which is 1. It goes away, right? And if this f of x is x, then that's going to be x, and this is going to be 1. So you get 1 over x times 1, which is 1 over x. This is the most general formula that you can learn. And it covers every single base under the sun. This is a special case. And this is a special case because they only deal with the base e. Where over here you can have a 2 or a 7 or 1/2. You can have any base. Further, do not always linger and only linger on those that have just x. Because y equals x is a linear function, 45 degrees to the origin, and that's not the world around us, all right? We have parabolic motion. We throw something and you have all other functions under the sun. So this is the case that you are at least remembering, but then that's the one that has everything in it. It has a function and also any base. So this is how we take derivatives of log. And we are going to immediately work on the example. So what is the derivative? Hold on. What is the derivative? Log base 9 of sine x. Have fun.
Is that an 8 or 9 at the bottom?
9.
It's a 9. So in the one box, that's an 8. Is that 9? That's just a variable.
A. Is that how you write A?
No. It's like an A and then a bunch of Y's.
A. No.
It's a 9 now. It says like a 9.
If I write a 5, you will ask if it's S. 3. There you go. Yeah, and it's not a uncompleted B or something. Capital. Half finished. Just do it. So, what do? Very quick, right? The function that follows the log is sine x. So Control C, Control V. And then its derivative on top times ln 3 on the bottom. And we have cotangent x over 3, ln 3. If I had that ta-da button, I was pressing it right now. I gotta get that thing. That's true. Ta-da theater, really?
Are you taking a field trip? Closed on this.
Yeah, but it. There we go. All right, that will be featured from now on. Anytime when the problem is solved. No, I'm going to start bringing soundboard. Yep. All right, good. So we took care of the derivatives. So now, what do we know? We know the definition for ln x in terms of integrals. We know the basic properties which could be proved using integrals. We know the derivative of ln's and logs. And the next step is integrals, right? So what is the integral of ln x dx? And the answer to that is stay tuned, because that's chapter 7. Awesome. So we're done with that. Bless. The next, this line is not straight enough. All right. So now we're talking about exponential stuff. So, you know how you can write 1 in many other ways? You should really try and annoy people when it's 1 p.m. Someone asks you what time it is. You just tell them sine squared plus cosine squared. Because you can. Number 1 can be written as ln e. And we know the definition for ln, right? So technically, you can actually read that. What time it is? It's integral 1 to e 1 over t dt. Awesome. But you got to use this stuff somewhere, right? Annoying others would be one of the good outlets. And also establishing that mental superiority. So you have a definition for E, which is a really strange definition in terms, I mean, it works, we all know, but it is what it is. And now we have all of the other stuff that you already know. So all of the exponential properties that are there for E, like e to the x times e to the y is very good. E to the x divided by e to the y is very good. E to the x raised to the y is very good. And then what else do we have? E to the 0 is nice. And e to the 1 is perfect. So all of these properties of exponents. Now how much is 1 over e to the minus x? Yes. And how much is e to the x? Yep. So all of those properties hold. Now also, if you have ae to the x, it's going to be a to the x e to the x. And a over e or e over a, whatever, maybe e over a is better. So all of those are good. They use purple? Yeah. They got to color code these. So these are all of your algebra properties regarding E. We want to know calc. So, for $1 million, what is the derivative of e to the x? It's like $20 million already there. For $10, e to the f of x. Nice. So Control C, Control V, and then times the chain rule, f prime. But then, this one, A, not 9, A, stands for any base. You know how you on the keyboard you have any key? That A stands for any base. What would that be? Times ln A, nice. All right. So, cut and paste times the derivative times the ln A. Bueno. So that's the one that takes care of everything. It collapses again to any of the vanilla ones. So now you are ready to take what is the derivative of 16 to x squared minus cosine x? Because we can. As Nike will say, just do it. And that's it. Oh, wait, hold on. Much better. All right. Now, do you know integrals for these? Of course you do, right? So let's start with the most ominous one. What's the integral of e to the x? Nope. Aha. Okay, there we go. Yeah, that plus c. The great slayer. Now, guys, if you have e to some kind of function dx, can that be integrated? Yes. But what do we have to have? What do we must have? Nice, which is why I left the space there. And this is where you unleash u sub. So disclaimer here, u sub has been used. Do we have this for any base? Sure. Everyone happy?
Did you put in red as it just u sub? Is that what you meant?
Yeah, I put it there in red so you remember that you can't just integrate. If you just see e to the sine x in integral, just cry about it, because it cannot be integrated. E to the sine x cannot be integrated yet. All right. You will be able to integrate sine e to the sine x later in this class, much later in this class. But for purposes of chapters 6 and 7 or Calc 1, the whole thing, no. So you have to have this derivative. So if this is a sine x, then cosine x has to be there.
So if it's not there, that's the derivative function there. Okay.
Yes. Right? Derivative function, derivative pairs, there's the function, there's the derivative. So over here you actually have the derivative, which is 1, right? The derivative x is 1, so that's why it works so nicely. But as soon as you go a little bit south. And that's it, we're done. So follow his example, and after the break we'll do 6.9, which is on mathematical models. Bye, stream.